All right, let's talk about a language that is, and I'm not exaggerating here, the engine behind our high-speed digital world. I mean, from the stunning graphics in the games you play to the lightning-fast algorithms that execute financial trades, C++ is that silent, powerful workhorse that makes it all happen. So that brings up a really good question, right? In an age of new, shiny, supposedly easier languages, why on earth do the most performance-hungry industries on the planet still bet everything on a language that's been around for decades? Well, that's exactly what we're going to unpack. So here's our game plan. We're going to look at why speed is everything, how C++ wrangles modern computer processors, and the really delicate art of making sure everything happens at the right time. Then we'll see the amazing things this lets us build, and we'll wrap up with the core idea, the whole philosophy behind C++. Let's jump in. Okay, so at the very core of all this is one simple, relentless demand: pure, unadulterated speed. For a whole class of software, think real-time graphics, huge scientific simulations, performance isn't just a nice-to-have. It's the entire reason the software exists. And this really comes down to a tale of two philosophies. On one hand, you have most modern languages. They're built to make the programmer's life easy. They manage memory for you, they smooth over the rough edges. C++, though, it's on a totally different wavelength. It gives you, the programmer, direct and incredibly fine-grained control over the machine. It trusts you to squeeze out every last ounce of performance. It's really the difference between driving a comfortable automatic sedan and strapping yourself into a Formula One car. And when we say speed, what are we even talking about? I want you to just look at this number for a second. Less than 1 nanosecond, a billionth of a second. That's the timescale a modern CPU lives in. That's how fast it can do something simple like add two numbers. C++ is designed to speak the language of the machine at that speed, to give it instructions without any fat, without any overhead. This is what people mean when they say C++ is close to the metal. But here's the thing. Getting that raw speed today isn't just about doing one thing really, really fast. It's about doing millions of things all at once. See, we kind of hit a wall with how fast we can make a single computer core, so the engineers just gave us more of them. And that multi-core beast, it creates a whole new world of challenges. Now, to get this, we've got to understand the difference between a process and a thread. Just think of a process as a whole application, like your web browser. It gets its own private sandbox of memory. Threads, on the other hand, are like individual workers inside that application. They all share the same memory, which is fantastic for working together. But it's also a recipe for total chaos if you're not careful. And that right there is the million-dollar question in modern programming. You've got 2 or 8 or even 16 of these threads, all trying to read and write to the exact same piece of data at the exact same time. How in the world do you stop them from stepping on each other's toes and turning your perfectly good data into, well, garbage? Because if you don't manage that chaos, you get into some really nasty situations. A data race is when 2 threads try to change the same thing, and the result is just corrupted. A deadlock, that's like a 4-way stop, where every car is waiting for the other car to go first. Nobody moves. They're stuck forever. And race conditions? Oof. Those are bugs that only show up some of the time, depending on the random luck of which thread got there first. They're an absolute nightmare to track down. So how does C++ help us dodge all this? It doesn't just throw its hands up. It gives us this incredible, precise toolkit for synchronization. It lets us play traffic cop for all those threads so they can work together safely and super efficiently. The 2 big tools in the box are locks and atomics. A lock, often called a mutex, is basically like putting a do not disturb sign on a piece of data. One thread grabs the lock, does its work, and unlocks it. If another thread shows up, it has to wait in line. It's safe and simple, but all that waiting can really slow you down. Atomics are a different beast. They're for tiny operations, like adding 1 to a counter, that the hardware itself guarantees will happen in one single, uninterruptible step. No lock, no waiting. And the performance difference? I mean, just look at this. It's wild. This chart shows us that if we use a standard lock, we can get about 30 million operations done a second, which sounds like a lot, But if we use a pure atomic operation, we hit 450 million. That's a 15 times speed up. This is why choosing the exact right tool for the job is so important. So why does this tiny little detail matter so much? This quote really gets to the heart of it. A modern CPU is like an incredibly fast assembly line, a pipeline. It's always trying to guess what instruction it'll need next. If it guesses wrong, that's a mispredicted branch. The entire assembly line has to stop, get cleared out, and restart. It's a huge waste of time. C++ gives you the fine-grained control to write code that helps the CPU guess correctly, avoiding those stalls and tapping into its full, incredible power. Okay, so we've seen the absolute need for speed, and we've looked at the tools C++ gives us to manage all this concurrent chaos. So now for the fun part. What do we get for all this hard work? What can we actually build when we have this kind of raw power? Well, video games are the classic example, right? Every single frame, which flashes by in just a 16th of a second, the game's engine has to update every character's animation, simulate all the physics, check if anything bumped into anything else, handle your input, and draw a whole beautiful world on your screen. That is a massive orchestra of tasks all running at once, and C++ is the conductor. And it's not just about brute force speed, it's also about being incredibly smart with resources. I love this quote. It's about a clever trick where, by sharing data in a specific way, a game can have a huge horde of zombies on screen, but only use the memory for a few of them on the graphics card. It's that kind of precise control over memory that lets developers build these huge, detailed worlds we love to get lost in. But it's so much more than just games. C++ is the default choice in so many other cutting-edge fields, where every nanosecond counts. Let's take high-frequency trading. A limit order book is just the master list of all the buy and sell orders for a stock. C++ systems are engineered to watch this list, process changes, and react in microseconds, a millionth of a second. Because in that world, being a millisecond too slow can literally mean losing millions of dollars. And how about AI? We usually think of AI running on some giant server farm in the cloud. But because C++ is so incredibly efficient, it's what makes powerful on-device machine learning possible. It lets your phone or your car or your smartwatch run really complex AI models all by itself without needing to call home to the internet. That opens up a whole new world of instant, reliable, and private smart features. So let's kind of pull back and bring this all together. From games to finance to the AI in your pocket, the common thread is a relentless demand for performance. And that performance comes directly from C++'s core philosophy. Trust the developer and give them total control. This quote really nails the central bargain of C++. The language basically makes a deal with you. It says, I'm going to give you immense direct power over the hardware. In return, I trust you to write code that is logical and correct. When you hold up your end of that deal, the compiler can then look at your code, prove that its optimizations won't break anything, and then it can just unleash the full terrifying power of the hardware. It's a partnership. And that leaves us with one final thought to chew on. As our digital world gets more and more complex, as we demand more immersive realities, faster systems, and smarter devices, does that deep, precise, low-level control over the machine actually become more critical than ever before?